the previous video, we went through the Playfair ciphers theory, and I gave you a little homework assignment. Now, in this video, we're going to go through the algorithm and ensure that each part is catered for. To start off, we're going to import NumPy. So we'll be using NumPy arrays. That's why we need this. If you aren't familiar with NumPy arrays, just check this video on the top right. So import NumPy as NP. Then our keyword is Playfair. So our plaintext is hello. And now we want to remove duplicates in the keyword. So that is a prerequisite of the algorithm. So let's look at that now. So we're going to have a final keyword. So this will contain no duplicates essentially. So for each letter in the keyword, we are going to now check if that letter is contained in the final keyword. So if it's in the final keyword, then we shouldn't be adding it there. So essentially we just have unique keys in there. So to go through PL and so on. And if the letter that we're currently on is not in the final keyword, then it will be added to the final keyword. So the final keyword is currently an empty string. And once it reaches, in this case, once it reaches the second A, it will recognize that it is in the final keyword already. So it will not add it to the final keyword. So this only happens, or the addition into the final keyword only happens if that letter isn't there already. So let's confirm that quickly. So we want to make sure that the final keyword only has unique characters. So let's type this properly and print that out. So I'm just going to run the script, and this is what we have in our terminal. So I'm just going to bring this up. Okay, so there is our final keyword, and as you can see, it has no duplicates. All right, so moving along. So we are now going to move on to the next part, and this is where we form the matrix using this keyword and the rest of the alphabet. So to form the matrix, we are going to fill in the first few spots using the keyword, and the rest of it will be the letters of the alphabet that are not in the keyword. So the letters of the alphabet that are not in the keyword. So forming matrix using keyword and the rest of the letters in the alphabet, something like that. I'm just putting comments so that we can clearly distinguish our sections. So the matrix will be made up of each letter in the final keyword. So this is just a list of each letter that's in the keyword, and then the alphabet will essentially be, we covered this in one of the first Python videos in this series, and this just uses ASCII values to form the alphabet. So converting ASCII values into characters, and this now has A to Z, and you can confirm that for yourself. We've already done that in the previous video. So now we haven't added the alphabet into our matrix. The matrix only contains, so we can confirm that quickly. We can at least confirm that the matrix currently only contains the keyword. So it's not a matrix yet, technically, but that list only contains the keyword, as you can see. So our aim now is to convert that into a matrix. So we have to add the rest of the alphabet, which is not already contained in the keyword or the final keyword. So for each letter in the alphabet, if the letter we encounter is J, so we want to skip J, firstly because it's already in the keyword, but in any other case, we'd also skip it because I just want to use I. So it's up to you whether you want to use I or J, but in this case, we have an I, and I guess I is commonly used. So we're going to skip J because we don't want to add it to the matrix, right? So that's what the continue is for. It'll go to the next letter in the alphabet. Else if the letter is not in the matrix. So remember that that matrix is just a list right now, and it only contains the letters of the final keyword. So if the letter that you're currently on in the alphabet is not in the matrix or the list, then you are going to append that letter to the list. That's what this is for. All right. Then in the end, we expect our matrix to now contain the keyword as well as the rest of the alphabet. But as I said, it's currently not a matrix, well, at least in terms of its shape. So let's now shape it into a 5 by 5 array. And this is how you do that using NumPy. Then let's print this matrix to see what it looks like. And here's what it looks like. So you can see the first few entries are final keyword. So Playfair without the A, because that would be a duplicate. Then the rest of the alphabet in order. So A, B, C, D, but you exclude everything which is already in the keyword, and you continue all the way to Z. So this is our matrix at the moment, and this is what we had in the theory section as well. Well, not really, because we used monarchy there, but this is the final matrix which you expect to have using Playfair as your keyword. Okay, so the next step is to pair our plaintext letters. So that's our next step. So we need to pair them so that we can use them and the matrix to get the ciphertext. So we're going to pair plaintext letters. There are definitely many ways to do this, but I decided to go with the following. So I want to remove spaces in my plaintext just to cover the general case, because the plaintext can be a sentence, right? So it won't always be a single word. So in the case that it is a sentence, then that's how you'd remove the spaces in the sentence. Then once everything is as you want it, so without spaces, then you can start forming your plain text pairs. So I decided to store them in a list, and that's what I'm just going to go with. So this list is currently empty, and it will contain all the pairs. So for our hello case, we expect it to have HELLO, but if you look at this has duplicates, so we have to deal with that. So this has to be LXLO in the end. So this is our final set of pairs, right? HELXLO. This is what we expect this list to have in the end. So we have to do two things. The first thing is we have to pair the letters. And the second is we have to check for duplicates. If there are any duplicates, this is how we deal with them, as we covered in the theory. Okay, so for that, I'm going to use a variable I just to loop through each of the letters in the plaintext. And I'm going to look at the current letter as well as the next letter. And since I'm going to using both indices, I want to end at one less of the final length. So in other words, my text is hello. I want to check H and E at the same time. Then once I reach the end, I'll check L and O at the same time. Just so I don't go out of bounds, then I need to make sure that my stopping condition is length less than 1, so that we don't go all the way to O, then try to reach out to another letter which does not exist after O. Okay, so this is why I'm saying while my counter is less than plaintext minus 1. So instead of just the length of the plaintext, I'll go for plaintext length minus 1. And I already explained that. Then I am going to say or check for duplicates. So if my current letter is equal to the next letter after it, then we have duplicates, right? So that's when we have duplicates. So I am going to now add to the list my current letter and an X appended to it. So that's what we're going to do. So coming back to our hello, H and E are not the same, so this if statement will fail. L and L are the same. So in the list, I'll now have HE, and then it will go in the if statement because L and L are the same. So if L, the current L, is equal to the next letter, which it is. Then we're going to append the current letter, which is L, plus an X. Right? So that's what we're going to do. But we haven't dealt with that second L. So to make sure that our loop deals with it, we're going to increment this by 1 so that the next iteration looks at L and O. So that's what we're going to do over there. Otherwise, if we don't have duplicates, I guess you can add a comment here, just say duplicates found, then you're going to add an X and then form a pair out of that. Otherwise, if you don't have duplicates, so no duplicates, something like that, else, then we are going to just pair the two. So you're just going to take the current letter and the next one, just like H and E. So H and E are not the same, so we're just going to add H and E to the list of pairs. So that's exactly what we're going to do. So to the pairs, you're going to append the current letter which you're dealing with, as well as the one that comes after it, because they're not duplicates. But now we've used up 2 letters, H and E, for example, and you wouldn't want to check E and L again because E is already in the pairs. So you have to skip 2 so that your next letter is L and not E. So in that case, we're just going to skip 2 over there and you move along. All right. So it's going to go through everything and we expect it to have everything sorted there, but not quite. Let's look at our plain text pairs at the moment if we just go through everything. So I'm going to run the program just to show you something that's a bit interesting. And we seem to have run into an error. Let's see what the error is. It says list index out of range. So what did I do or what did I not do? So starting at 0 and length of that one is 1. And then I'm checking if this is equal to that. And then plain text appends that. Okay, so this should not be plain text pairs. So we're adding the current letter in the plain text to X, and we're adding the current letter in the plain text to the next letter in the plain text. So that's a mistake which I made over there. That's why we're getting a list index out of range error. So let's try that again. If I run that, then this is what we have. We have HE, LX, LO, which is what we expect. But there's another case which we might have. Let's change our plain text to there. So we want to cover all cases and not just this one example that we have. So if this is there, you can see that the pairing will be TH, ER, and E. We don't want the E to be by itself, and I'm just going to run this so that we walk through the solution for such a case. So if you look at this, we only have TH, ER, and a missing E because it's not a pair, it's just by itself. So what do we do then? We need to include that as well. What we can do is we can add an X to it, but these 2 conditions obviously don't cater for that. So after the while loop, we're going to check that the pairs match what we're expecting. So if the length of our plain text pairs, so the number of pairs that we have there, times 2 is less than the length of the plain text. So using this as an example, the length of our plain text pairs is 2 because we have 2 entries in the list. So 2 times 2 is 4, but our plain text has a total length of 5. So this is a good condition to check if there's a single letter that has been left out. So we're just checking that the length of the plain text pairs times 2 is less than the plain text length, and this will pass in the case of there. We are going to now add the last letter in the plain text. So this is how you access the last letter. You use a -1. That's one of the ways. And you're going to add an X to it so that in the end, when we print out our pairs, so we ran into another error. List object is not callable. So what did I do? I did not append. I tried to turn that into an index, which is obviously not allowed. Okay, so now we have THEREX, and this is what we'd expect, and everything is paired up and ready for encryption. So if you ever have a letter which is outstanding or left just on its own, then this is what you have to do, right? In our hello case, this is not the case, but yeah, just look out for that. So let me just make everything lowercase just so we don't run into issues. And then, yeah, that should be fine. Otherwise, you just have to manually change everything to lowercase so that it syncs up with your ASCII values and everything else that's happening. Okay, so now let's trace back. We've removed duplicates in the keyword. We formed the matrix out of the keyword and the rest of the alphabet. We formed our pairs out of the plaintext, and we are now ready for encryption. So let's start the encryption process. Encryption. And in the next step, we're going to go through each case, right? So the first case is, so let's first form a variable called ciphertext. The first case is when we have the letters in the same row. And I think hello actually helps us to go through each different case. So let's have a look at our matrix to see the different cases that are involved here for using our keyword Playfair and our plaintext hello. So this is what the matrix looks like. Let's look at H and E. H is over there, E is there. So we have the first case where they are in the same row, as you can see. So that's one case. So we're happy with that. Then we have L and X. There is L and there is X. They're neither in the same row nor column. So that's the third case. And let's see if we have some in the same column. So L and O, we do have an L and O. So we have all three cases in the case of hello, which is a coincidence, by the way, but that'll help us to confirm our ciphertext or to confirm our algorithm. So let's get right into it. So the first condition, so we're going to go through each pair in the plaintext pairs, and I want to add this variable just so we don't waste time processing stuff that has already been handled. So if we found the letters in a row, we wouldn't want to now move on to the column computation or the last one. So I'm just going to use this so that we go out of the loop and we go to the next pair. So if they're in the same row, this is what you're going to do. Well, at first, you don't really know. So you're going to loop through each row in the matrix, literally. So for row in range 0 to 5, we want to check if the pair is in the same row. So if the first letter is in the row that we're dealing with right now in the loop, so this extracts the whole row. And the second letter in the pair is also in that same row, then we're going to apply the theory, which says you're going to take the letters which are to the right of each. All right, so you're going to go back to a matrix and then figure out what that's supposed to look like, or manually find the correct ciphertext. Then we're going to print that from our code to confirm that it's the same. Okay, so the first letter index. So we need the index of the first letter so that we can go to the right of it. We also need the index of the second letter so we can also go to the right of that. So now we're going to make a list out of the current row that we're dealing with so that we can just use one index. So it will be a list, and then from that we can go to the right in that list. Okay, so that's another way of explaining it. So matrix in the current row, we're making the current row a list, and we want to find the placement of the first letter, and we're going to do the same for the second letter. So second letter index, would be found by, I guess we could have it's not really necessary to eliminate redundancy. We could say current row equals to this. I guess we can do it everywhere. That's crazy, but let's do it. Okay, so this is our current row, so that we only do it once, and this makes sense. So if the first letter is in the current row, and I guess this helps us to understand our code better. So that's how you'd extract the current row, and we're just going to have it everywhere instead of retyping this. Okay, I think this is better. Okay, so if the first letter is in the current row, this is readable as well. I like this. So if the first letter is in the current row and the second letter is in the current row, so we're looping through each pair, then we are going to take the index of the first letter and the index of the second letter as well. So one would argue that we should have made variables out of the first and second letters, but that's just a bit too much. So let's continue with this. We have the indices of both, and we can form the ciphertext by going to the right of each. So in the current row, we're going to go to the right, and going to the right would mean we are adding the columns. So we're staying on the same row, but we're adding one to the current column. And I'll show you in the matrix as well, but you can visualize that for yourself. And we're going to make sure that we apply a modulus 5 so that it can wrap around in case that our letter is all the way at the end of the row. So that allows us to wrap around. So that's the value of the row, and that's the whole thing there is the column that we're dealing with. So we're moving to the right to find the ciphertext. And we're going to do the same for the second letter. Ciphertext would just be the letter which is to the right of the second letter index plus 1, then modulo 5. Okay, so going back to our matrix, let's print the matrix, do this by hand, then see if our code does what we expect it to do. So let me quickly run this. This is our matrix once again. In the case of HE, H is there, E is there, so they're on the same row. So we expect the ciphertext to be KG, because this is to the right of H, and this is to the right of E, right? And that's what I meant when I said we're incrementing the columns. So E is currently on this column, the first one, and if you want to move to the right, you're on the same row, but you have to add one to the column, and that's what these lines do. Okay, so that's what we found manually. We expect HE to be replaced by KG. So let's confirm that quickly by printing the ciphertext after all of that. So we're going to print the ciphertext. I'm just going to clear my terminal, rerun this, and if you look at the ciphertext which we just printed, it says KG. So we're happy with what our code does so far. So we can continue. And this is the case where the letters are in the same row. So our pair has been handled, so we don't have to do any processing on it anymore, and we can break the loop so that we go to the next pair. Because if we don't break that loop or that iteration, then it'll come to this code and it'll try to execute it again. That's just wasting time. We already dealt with the pair, so we might as well break out of the loop, then go to the next pair. So that's just my interpretation of this. You don't have to do that, but yeah, highly recommend it. So if they're in the same column, once again, let's just quickly print our matrix. So print matrix. Then we're going to go to the next case and see what's going on over there. So this is our matrix, and L and O, which are all the way at the end, are in the same column. So expect them to be replaced by R and V, because R is below L and V is below O. So that's what I expect over there, same column. So let's compute that. It'll be somewhat similar, just that if you're going to go down, you're changing rows and not columns. That's the only difference. So from L to R, you're going to maintain the column number, but you're going to change the row number because you're going to the next row. All right, so let's do that. You might pause if you want. You can pause this here and do it on your own. So let's get into that. I guess you can add an extra condition here. This breaks if that should break. Okay, that's fine then. So this break leaves this for loop, but not that one. So what I will do, so we do indeed need that extra variable. So that's fine then. So if we found it in an earlier row, or before we finish the matrix, then we can stop our computation. That's what that does essentially. So now out here, that break will leave this for loop, but it won't go to the next iteration of that. So we need this. All right, so I thought I had messed that up for a bit. So after that, we need this pair handled variable so that it goes to the next iteration of the pair, because this break here only breaks this for loop, but not the for loop that goes through the pairs. Okay, so we need to continue there just to get out of that, or go to the next iteration so that we ensure that it doesn't try to compute the column stuff after doing the row stuff. There's no need. We already found it in the rows. There's no need to look for it in the columns as well. Well, at least for the current pair that we're dealing with. So now we're going to deal with the current pair. And to do that, we're going to do the exact same thing as I said, but now we're going through columns. And we want to check if the letters are in the same column. And once again, we're going to have current column, and that would be matrix, and the rows can be any, and that's how you extract the whole column. Setting the rows to any, then extracting or specifying a specific column. Then we're going to do a similar check if the first letter in the pair is in the current row, not the current row, but the current column, and the second letter in the column is in the current column, then we're going to find the index of each once again. So we're going to find the index of each letter in the pair, starting with the first letter, then the index of the second letter as well, second letter index. Then we are going to now form the ciphertext out of these. So the ciphertext would be formed by us going down. So it's still the same thing essentially. So we might as well copy paste this because it's literally the same thing. So I don't recommend copying and pasting codes because that's how you make mistakes. But in this case, I guess we can work around it, because here, this is a change in rows. So that has to go. And we don't have the row variable as well. And then we also want to keep the column as it is. So we're on the current column, we're changing the row number because that's how you go down. To go up or down, you change the row, and that's why that section is now on the left and the column stays the same. Okay, so just look out for that. Then pair handled will be set to true once we found these, so that we don't continue doing anything that's below this, at least for the current pairs. So once again, if pair handled, we're going to continue to the next pair. Okay, so let's fix our indentation there. Then continue to neither same column or pair. And this is the easiest one, well, not the easiest one, but the quickest one. So neither same column nor row, and this is when you take the letter that's on the same row as the letter you're dealing with, but on the same column as the one next to it. So in the case of, let's print our matrix. In the case of, I think LX, but we're going to see that in a bit. Okay, so I don't know how we got to this, but look at this error. This says if the first letter in matrix in current column, that's clearly an error. All right, so if the first letter is in the current column and the second letter is in the current column, that's what it should have been. That's where the error comes from. Okay, interesting. All right, so let's continue. So I was saying, if we print the matrix, this is what it looks like now, and L and X are in different rows and columns. So L will be replaced by Y because that's on the same row as L, but on the same column as X, and X is next to L. Then X will be replaced by V because V is on the same row as that, and V is also the same column as L, which is next to X. So that's how you do with LX. So this is what our code will do in this section, in this little section, which is the last section actually. So almost done. So we're going to find the coordinates of each of them. And in this case, we're not going to use a single index. We need the coordinates so that we can figure out which letter is on the same row as them, but the same column as the other one. That's literally all we're going to do. So we want a place where the matrix is equal to the first letter. And that's how you'd find its coordinates. And then the second letter coordinates would be a place in the matrix where the matrix is equal to that letter, which is the second letter. Okay, so we're going to do the first letter replacement. Yeah, and the first letter in the ciphertext will be replaced, as I said, by the letter which is on the same row as it is. So you'd extract that using 00, an index of 00, and then you'd want it to be replaced by that letter which is on the same row should be on the same column as the second one, and you'd extract the column using 1 0 from that. Okay, so that's literally it. And we're going to do the same for the second one. So the second letter replacement would be ciphertext plus equal to in the matrix where this letter has the same row as our second letter, but it has the same column as the first letter. Okay, then after all of this, we expect our keyword. Well, our keyword hasn't changed. Or let's just print our final keyword and let's print it together with the original keyword. Actually, that should be interesting. So not really, but yeah. Plaintext is plaintext, and the final keyword is that. And then the initial keyword, I guess you can have it like that. Then will be keyword. Then finally, we're going to have our ciphertext, the final ciphertext after all of this, because it's now combined. Okay, if you want, you can just capitalize this stuff or just split this as well. It's totally up to you. Then we can print everything by running the program, and that's the result that we get. So that says plaintext hello, initial keyword Playfair, keywords, which should have been final keyword but doesn't really matter, is Playfair without an A. Then our ciphertext is KGYVRV, and if you remember from our manual computation as well as the homework in the theory section, this is what you expect to get. So this is how you do the Playfair cipher in Python. At least this is my interpretation of it, and I hope you're able to follow along. If you have any questions, feel free to leave them in the comment section. For now, like, share, subscribe, and I'll see you in the next video where we'll cover yet another algorithm.